Next, requirement for performing a dynamic analysis. What are the requirements which the Eurocode specifying to perform a dynamic analysis? Here they have given a flow chart. So this flow chart, don't worry, don't go into detail. Let me explain like briefly how they set up this one. So if you start this one, if the speed of the train is less than 200 kilometer, then yes, if it is yes, then we need to go check whether the bridge is continuous or not. If it is continuous, then dynamic analysis is not required. Then we can use the one static formula to compute the dynamic factor. But if it is not a continuous bridge, then we need to refer this graph, this chart, and we need to check whether there are natural frequencies within these two upper bound and lower bound. If it is within that, then also the dynamic analysis is not required. But if it is outside that, then the dynamic analysis is required. This is for case less than 200 kilometer. If the train speed is more than 200 kilometer, then if it is a simple structure span greater than 40 meter, then the dynamic analysis is not required. We need to use this table. But if it is a simple structure span, not if it is not a simple structure, it's continuous or something, then the dynamic analysis is required. Something like this. It's a process is like this. But anyway, is the condition we can perform a dynamic analysis, because getting a dynamic analysis instead of using the formula will give a economical design, because the dynamic factor plays with many parameters. So if one parameter changes, everything will change, because in a particular project there will not be a same span for throughout the entire length. A particular project, let us say a 1 kilometer bridge is there. It may not have only 30 meter span, multiples of 30 meter span. It may have 20 meter span, 30 meter span to overcome some obstructions underneath the road. So it is like that. So if for each span, the dynamic factor varies. So if you can compute each span the dynamic factor and apply it in your design and design the structure means, then it will be an economical design. Instead of doing for a maximum case or a minimum case, something like that, and averaging it may overlook sometimes, it may happen. So it is better to do a dynamic analysis for any case, for any kind of span in a particular project. Then the first one is the process where they are mentioning how to where to do the dynamic analysis. Second one is when doing the dynamic analysis, these are the requirements. The first one is the loading. Loading is the vehicle load, that means the train load. In Eurocode, what they have given is they're given two options. When it is a real train means whatever the train they are going to brought from the supplier and they are going to run it over the track, that is a real train. If that is the case, then they can use the wheel configuration, wheel load from the train. But in many projects, what happens when they start doing the project, designing the project at the design stage, they may not fix the system contractor, that is a train contractor. So they may not know the configuration of the wheel. So in that case, what happens? The Eurocode has given certain wheel load, axle loads. So if you see the left side, for span less than 7 meter, they have given one type of wheel configuration. That is that they are mentioning as HSLM-B. That is high speed load model B. For span greater than 7 meter, they are given like a 10 sets of vehicles. This is because this is to cover all types of high speed rails in the world. So they are given some 10 wheel configurations, like from A1 to A10. When the span is greater than 7 meter, we need to check the dynamic behavior for all these wheel loads. Then next one, dynamic analysis calculation, the value of mass associated is self-weight. Then if ballast load is there, the ballast load means the ballast over the deck with the track, everything, those things, and with the vehicle load. Vehicle load is usually, if you can see some rail projects with the viaducts, there will be a 2-on-4 rail track will be there. One from place A to B, and the other track will be from place B to A. So it will have majorly it will have 2 tracks. So, but for the dynamic analysis, if the one track is loaded, then it will govern the dynamic factor. So the code suggests to only load one track with self-weight, ballast load, everything. This is the loading. Then speed to be considered. In our dynamic analysis, what we usually do is we will run that the vehicle load like by performing a time history analysis from minimum speed to maximum speed. The minimum speed is 40 meters per second. That is because this one is they are showing only for high speed train, so it comes around 140 kilometer per hour. But for normal train, we can start from even from 0 kilometer per hour or 1 kilometer per hour to the maximum speed. Maximum speed, what they are telling is it is 1.2 times the maximum line speed. For example, in case of metro rail projects, the maximum line speed will be 80 kilometer. So 80 multiplied by 1.2, that speed they will consider for performing the dynamic analysis. So what they will do is they will start from 1 kilometer per hour, and they will increase the with the interval of 20 kilometer per hour, 40 kilometer per hour, and up to the maximum design speed. So like this, they will perform the dynamic analysis and they will found the deck acceleration impact factor from that. Then the third one is the resonance speed. This is very important. This resonance speed we can calculate using this formula, or when we perform the dynamic analysis, we can found where the deck acceleration is excited. So that is the point where the resonance speed occurs. So from the dynamic analysis, if we perform the dynamic analysis, we can straight away get the value, the resonance speed. But if it is a simply supported, we can use this formula, Vi equal to n naught into lambda, where Vi is the resonance speed in meter per second and n naught is the first natural frequency of the unloaded structure. When the structure is not loaded and if we perform an eigenvalue analysis, then we can find this resonance speed for a simply supported bridge. For a continuous bridge, we need to perform a dynamic analysis. But this formula they are given just for getting an idea. Then, as I mentioned earlier, we have seen the speed, mass, then damping. Damping is based on the type of bridges. Here they have given like 3 types of bridges: steel, composite, pre-stressed, filler beam, reinforced concrete. For each type, based on the span, we can compute the damping factor. This one we can use in our time history analysis to perform the dynamic analysis. Then the mass. Here the mass, as you see, we can vary the mass because the self-weight of the structure is constant, so we cannot vary that one. The live load also is constant because the different train we need to do that one, but it is a constant value for a particular case. But in case of a ballasted track, the track sometimes can get wet, so that the load will increase, so that we need to do for dry case and wet case. So the code specifies that for lower bound estimate the mass to predict maximum deck acceleration using minimum likely dry density and minimum thickness of ballast. The second case, the upper bound to predict the lowest speed at which the resonance effect are likely to occur using maximum saturated. When it is saturated, the ballast, and dirty, then this is the upper bound. For these 2 cases, we need to perform the dynamic analysis. Then the final one is the verification. Once we have done by assuming all these loads, mass, damping, and we perform the time history analysis, and if we get the output, the deck acceleration, it should be for like this. It should be less than this one. For ballasted track, it should be less than 3.5 meter per second, and for slab track, it should be less than 5 meter per second. Now you can see the difference between slab track and ballasted track. First, let me explain you what is the difference between ballasted track and slab track. Ballasted track, as you know, like there will be a ballast over the deck, over that the sleepers will be there, over that the rails will be laid. That is the ballasted track. The second one is slab track. What they will do is, if you have carefully watched the metro rail, the guideways or something, they have the guideway, the deck, over which they will have the reinforced plinth under each track. Over that the rail will be laid. So that is slab track. So in case of slab track, there is no moving object. But in case of ballasted track, there is moving object. The ballast can move because it is like this just laid over the deck. So when the train runs, and the deck will start accelerate. During the acceleration, if the deck accelerates more, there is a chance that the ballast can thrown away or displaced from the deck. So to avoid that, the ballasted track has stringent value. It has a lesser values. There the deck acceleration they are controlling very much to 3.5 meters per second square. But for slab track, since there is no movement, no moving objects over the deck, no moving object, that means no ballast or something, no material, something that can move, that can displace. So the slab track has a lesser stringent value. It is 5 meter per second square. Then for computing the dynamic factor, this is the formula. This is nothing but a maximum deflection value. Y dyn is y dynamic by y static. So that by performing the dynamic analysis for each load case, the maximum deflection at the superstructure, the span, that is the value we need to put here. And for the static load, static case, when the moving load is not moving and it is in one place, for that we need to compute the deflection and we need to put the deflection value here. Then this will give you the dynamic factor. This one we need to use in our static analysis and increase the vehicle factor, and we need to perform that analysis, the normal analysis, and we need to design the structural elements. Up to this we have seen the how we are estimating impact load for bridges and bridges. Now let us see how we are going to estimate the current practice, the industry practice which we followed for estimation of seismic load for both bridges and buildings. Here we follow basically two methods. The time history analysis is the third method, but usually for bridges, those things, buildings, we follow these two methods. First one is the elastic seismic acceleration method. The second one is response vector method. Let us see the elastic seismic acceleration method. What I am doing here is I am just comparing both codes. Both are Indian codes. Here I am again coming back to Indian code. On the left side is the code corresponding to bridges. The right side is the code corresponding to buildings. That is, left side for bridges is IRC, Indian Road Congress 6 2017, and for building it is IES, Indian Standard 1893. So what are the formulas which I have given? I am sharing here. So if you see for the design horizontal seismic force suggested by both the codes are same. Both the formula is the seismic coefficient formula is Z by 2, the zone factor. Then I by R, the I is the important factor, R is the response reduction factor, SA by G is the average response acceleration coefficient. Both codes shows the same. This is the major formula where we can compute the seismic coefficient for a particular region, because the different zone has different zone factors. So that we see in this slide. This zone factor is taken, the Z value zone factor is taken from these two tables. Both the tables are same because the zone factor for the particular region in India is same. The third one is the importance factor. Importance factor is the I value. The I value for bridges is different. The I value for the building is different. So this one we need to refer. If it is bridges, you need to follow this one. If it is building, we need to follow this one. Here we have some difference. Before that, we don't have any difference, but from here we have some difference. Importance factor, we have difference. The fourth one is the SA by G. This one mainly depends on the soil type. Because the seismic, as I earlier mentioned, it is due to the ground movement. So the soil is playing major this one. So the soil structure interaction is very, very important. That is captured here on the SA by G value. So the code gives like this, the two values, both for bridges and buildings I have shown here. But this value is mainly depending on the time T value. So T value, the bridges, it shows it can be found from this formula, and for building it can be found from this formula. So it predicts this SA by G value based on the time period of structure from 0 to 4. The SA by G value can be found, and similarly for buildings also it can be found. Once we found the time period of structure, we can found this one. Then the next one is the response reduction factor. For bridges, based on each component's material type, the response reduction factor is different. And similarly, in case of building, based on the moment resting frame or steel frame, based on that, like if we do some ductile detailing, the shear and seismic enhancement will be there. So the response reduction factor will be more, something like this. They have suggested some value. So these are the things. Up to now, they have seen the elastic seismic acceleration method. Then now we see the elastic response spectrum method. The elastic response spectrum is is just one step forward, one step from that. Because what you do is there is this seismic value based on the soil type and time period. We will find this value, AH value. But in case of elastic response spectrum, what we will do is we will plot this graph based on different time period and soil type, because for a particular project the soil type will be of one type, and based on the n value and the time period of structure from 0 to 4 seconds, we can plot the seismic coefficient by doing this one. And this graph we can input as response spectrum method in any software, and we can perform a response spectrum analysis. So what the software will do is, yeah, I'll show in the next slide. What the software will do is it will do an eigenvalue analysis to find the mode shapes for natural frequency and time period, and finds the natural frequency and time period. What it will do is it will do the eigenvalue analysis to find all the mode shapes, those mode shapes like lateral sway or longitudinal sway or torsional twist. Those things it will do, like an 15 or 20 mode shapes it will do, and find and obtains all the first and higher mode shapes, and those mode shapes it will combine and finds the design force. This is very appropriate method compared to the earlier one. It is like a more conservative approach, but this one is like an appropriate method, because if you see a structure like example a building in a longitudinal direction, when the seismic force is applied, it may deform in a different way. But if the seismic force is applied in a transverse direction, it may deform the other way, because based on the stiffness, EI, the rigidity controls the stiffness of the building. So based on that, the mode shapes will be different. So doing the elastic response spectrum will be more appropriate. But doing this one will take some time. But for small jobs, small bridges or small building, we will do the earlier method. And that one also I will share you how we need to find which method we can go. This is the current industry practice. For impact load and deck acceleration, I am going to the earlier one. I am going to share you how the current industry practice has been done, because the previous slides, what I have been explained is how we are performing the analysis and how we are predicting the impact factor, seismic force, and we are designing the element. Now let me share you how we are doing in current industry practice. For impact load or deck acceleration, for a highway bridge, we straightway use the code, and the code has a graph based on the vehicle type, and from that we derive the impact factor. In case of railway bridge, we purely do based on the dynamic analysis. In some projects, we will use the formula given in the code itself, but that will come around 20%, that one. But usually we will do a dynamic analysis and find the impact factor and deck acceleration. This is what the current industry practice they follow for estimating the impact load and deck acceleration. The next one is a seismic force. When it comes to seismic force, we have seen the two methods, elastic seismic acceleration method and elastic response spectrum method. The first method and second method, I will show you where it will be used, which method where it will be used. For bridges, if it is a simply supported bridge, we will use the first method, the simple method. But if it is a complex bridge, like a continuous span or curved in span, curved bridge or something in plan, then we will use the elastic response spectrum method. In case of building, for a regular building, when the building is lying in the zone 4 or 5, if height of the building is greater than 40, then we will use the elastic response spectrum method. And for zone 2, if it is greater than 90, we will use the elastic response spectrum method. If it is less than 40 or less than 90, we will use the earlier method. For irregular shapes also, only the difference is height. If it is greater than 12, we use the elastic response spectrum method, or less than 12, we will use the first method. For zone 2 and 3, if the height is greater than 40, we will use the elastic response spectrum method. If it is less than 40, we will use the first method. For all other building, small building, we will use elastic seismic acceleration method. So this is how we are using this one. I think now I am coming to a conclusion. Now let us see what is the career path and job opportunities by knowing this knowledge. As you see, railway transportation sectors are booming with the introduction of new projects in even high-speed rail projects. Many metro projects in many major cities have been there, and they are extending the line, and they are proposing new metro projects in many major cities. Hence, having a knowledge of dynamic analysis for a railway bridge will be a value addition when you are applying for a job, or you can get a better job, because knowing this knowledge, because this dynamic analysis is not in our curriculum in our graduation or our masters. So if you know this knowledge before entering into a job, then it will be a value addition to us. Then the next one is knowledge gain on impact load assessment for a deck or value addition, and which are usually not covered in civil engineering graduation syllabus. Maybe some master graduation they cover, but during the graduation they will not cover. Then the third one is the seismic analysis of a building or bridge based on current industry practices will be a value addition when compared to a academic knowledge. Only knowing like academically about the seismic analysis, like it is a horizontal force acting during a ground movement. Instead of that, if you know what are the method followed in the current industry practice and how they compute and how they analyze, that will be a value addition when you are getting in a job. When you are attending an interview, you can explain the process, how it can be done. Then the interviewer can know your skill, those things. Thank you.